Transaction trends and seasonality in banking data. In this lesson, we will explore how to analyze real-world banking transaction data to detect trends and seasonality. Understanding transaction trends helps banks optimize services and detect anomalies early. Seasonality gives insight into customer behavior across different periods. You will use Python to visualize, summarize, and model banking transaction patterns. By the end, you will be able to identify patterns, spikes, and cycles in transaction data over time. No prior experience with time series data is required. Running the cell now. We import pandas for data frames. We import NumPy for numerical operations. We import matplotlib.pyplot for data visualization. We import Seaborn for stylish plots. We import warnings to suppress unnecessary alerts. We ignore warnings to keep output clean. We set random C to 42 for reproducibility. Running the cell now. Understanding the data for trend and seasonality. Our transactions table contains events linked to customers with amounts, timestamps, and transaction types. Common columns: transaction ID, customer ID, amount, type, channel, and date. Time-based columns like date and hour are crucial for trend analysis. Beginners often mistake random spikes for seasonality. Always visualize before concluding. Missing or duplicate dates can corrupt analysis. Always check your time columns. Running the cell now. We will create a synthetic table to simulate real banking transactions for this lesson. This part sets up the number of transactions. This sets up how many customers are in our dataset. We create our transaction data frame. We assign a unique transaction identifier for each row. We randomly assign each transaction to a customer. We generate a random but realistic transaction amount for each occurrence. We randomly designate each as a debit or credit. We randomly assign a transaction channel. We simulate hourly transaction timestamps for 1 month. We summarize all these columns into our data frame. We print out the shape of our data frame. We preview the first 3 transactions. Running the cell now. This output confirms our synthetic dataset has correctly generated 1,000 transactions with 6 key columns, including time-related date and categorical transaction underscore type and channel. Note how transactions span hourly timestamps starting from January 1, 2024, which sets us up to analyze trends and potential seasonality over time. Observing the first few rows helps verify data integrity before moving on to visualization and deeper trend analysis. Try changing n_transactions or n_customers to see how the dataset size changes. Checking data quality before analysis. Always check number of nulls, duplicated rows, and correct column types before touching time series data. Wrong or missing dates can break your seasonality analysis. Aggregations work best after data types and formats are validated. Running the cell now. We will inspect null values, duplicate rows, and column types to catch any data quality issues before analysis. We show missing value counts by column. We check which columns, if any, have null entries. We check and count duplicated records. We print a breakdown of data types for every column. This will help identify columns that need attention before time-based analysis. Running the cell now. This output shows that there are no null values or duplicate rows, confirming the dataset is clean for analysis. The data types are correctly assigned, with the critical date column as a datetime 64, ensuring proper handling of time series operations. This validation step is essential to avoid errors in seasonality analysis and to enable accurate aggregations later. What would you do if you spot any nulls in the date column here? A best practice for time series analysis is to use a datetime index. This line ensures all dates are in datetime format. This line sets the date as the index for easier resampling above. We display the name of the new index to confirm it is set correctly. We print 2 rows to confirm the new index. Running the cell now. This output confirms that the date column has been successfully converted to datetime format and set as the data frame index, which is essential for time series analysis. Notice the timestamps as the index and the presence of key transaction columns, ensuring the data is ready for accurate aggregation and seasonality checks. This step helps prevent errors related to date handling in subsequent analysis. Try removing the set_index line and see how some resampling functions may fail. Visualizing overall transaction trends. Visualizations help you spot trends or anomalies over time with ease. Aggregate total transaction amounts per day to observe daily changes. Line plots are great for revealing cycles or sudden changes. Running the cell now. Let us calculate the total value of transactions per day and plot the trend. We sum the amounts for each day using resampling. We create a wide figure for clear display. We plot the sum daily amounts as a line. We set the title for our plot. We label the y-axis as amount in dollars. We label the x-axis as date. We show the plot. Running the cell now. This line plot shows the total transaction amount aggregated for each day, making it easy to observe how daily totals fluctuate over time. Notice any peaks or dips that could indicate busy or slow transaction days, which helps in identifying overall trends or unusual activity. This visualization directly supports the lesson's goal of spotting temporal patterns in transaction data. Can you spot weekdays with higher transaction totals in the plot? Now we calculate the average transaction amount per day. This line computes the mean transaction amount for each day. We print the average amounts for the first week. Running the cell now. This output shows the average transaction value for each day over the first week of January 2024. Notice the slight day-to-day fluctuations, which suggest variability in daily spending patterns. By aggregating with .resample, d.mean, the code prepares data ideal for a line plot, helping us visually detect trends or unusual shifts in average transaction amounts over time. Does the average show a rising, falling, or stable trend week to week? Let us see how active each day is by counting the number of transactions. We count transactions for each day. We create a wide figure for the bar plot. We plot counts as a bar graph. We set the plot title. We label the y-axis as count. We label the x-axis as date. We ensure tight layout for readability. We display the plot. Running the cell now. This bar chart shows the number of transactions for each day, helping us quickly see how transaction volume fluctuates over time. Notice any days with noticeably higher or lower counts, which could indicate unusual activity or trends worth exploring. This visualization confirms how aggregating transaction counts per day provides a clear overview of overall transaction frequency. Try increasing n_transactions and watch how the counts per day increase in the plot. Now we look at the sum of transaction amounts per week to smooth out daily noise. We resample and sum by week. We create a wide figure for clarity. We plot weekly totals with dots at each week. We set the title for trend visibility. We label the y-axis as total amount. We label the x-axis as week. We show grid lines for easier comparison. We show the plot. Running the cell now. This line plot shows the total transaction amount aggregated by week, making it easy to observe overall trends and fluctuations in spending from week to week. Notice how the markers highlight weekly totals, revealing any consistent increases, drops, or irregular spikes. This visualization helps identify broader patterns over time, which is the key goal of resampling daily data into weekly sums. What is the biggest week-on-week jump or dip you see? Seasonality often appears on certain days of the week. Let us check for this pattern. We add a column for the day name. We get the average amount for each weekday and order them. We create a wide figure. We plot averages as a bar chart using Seaborn. We title the chart to clarify what is shown. We label the y-axis for transaction size. We label the x-axis for days. We show the plot. Running the cell now. This bar plot displays the average transaction amount for each day of the week, highlighting how spending varies across weekdays. Notice the clear differences in height between bars, which help identify patterns such as higher or lower average transaction values on specific days. This visualization connects to the lesson by revealing potential seasonality or consistent trends within weekly cycles that aggregate daily totals alone might miss. Which day has the highest average amount? Are there patterns around weekends? Let us smooth short-term fluctuations using a 7-day moving average. We calculate the 7-day rolling mean. We create a wide figure. We plot the actual daily total. We plot the 7-day moving average as a red line. We highlight the main trend with a title. We label y-axis as the total amount. We label x-axis as date. We add a legend to explain lines. We display the plot. Running the cell now. This plot shows daily total transaction amounts alongside a 7-day moving average, smoothing out short-term fluctuations to highlight overall trends. Notice how the red line reveals clearer cycles and gradual changes compared to the more jagged daily totals, helping you better understand underlying patterns in transaction activity over time. This technique is key for spotting trends or anomalies that daily data alone might obscure. Use a different window like 14 or 21 days and observe the changes in the trend line. Advanced analysts often want to flag days with abnormally high or low transaction volumes. We find the first quartile, 25th percentile. We find the third quartile, 75th percentile. We get the interquartile range, spread between 25th and 75th percentile. We set the upper bound for outliers using 1.5x the IQR rule. We set the lower bound for outliers. We identify days where the transaction sum falls outside typical range. We print the days which are likely outliers. We display the outlier amounts and their dates. Running the cell now. This output shows that no days had transaction totals considered outliers based on the IQR method, meaning the daily sums fall within a consistent range without extreme spikes or drops. In the context of visualizing overall transaction trends, this helps confirm the daily transaction amounts are fairly stable, with no unusual anomalies disrupting the pattern. Identifying outliers is crucial to ensure that the trends we observe are representative of typical behavior, not skewed by rare, extreme values. Are more outliers on weekends or weekdays? What could explain these outlier days? Heat maps reveal at what days and hours transaction activity peaks. We add an hour column extracted from the index. We create a pivot table of average amount per weekday and hour. We order days for visual consistency. We start a wide figure for the heat map. We plot the heat map to show amount size per hour and day. We title to show what the map means. We label y-axis for the day. We label x-axis for the hour. We display the plot. Running the cell now. This heat map reveals how average transaction amounts vary across days of the week and hours of the day, highlighting daily patterns and peak transaction times. Notice the color gradients indicating higher averages on certain days and specific hours, which helps identify when transaction activity intensifies. This visualization complements the lesson by showing how aggregating and plotting data by multiple time dimensions can uncover detailed temporal trends. Look for dark blocks. Are certain hours or days much busier? Time series decomposition helps separate signal into trend, seasonal, and random components. We import a tool to break time series into components. We decompose with a 7-day period for weekly patterns. We plot all components, observed, trend, seasonality, and residuals. We give a super title for clarity. We display the component plots. Running the cell now. This plot breaks down the daily transaction totals into trend, seasonal, and residual components, helping you clearly see the underlying patterns over time. Notice the smooth trend line showing overall growth or decline, the repeating seasonal pattern reflecting weekly cycles, and the residuals capturing irregular fluctuations. This decomposition deepens your understanding of transaction trends beyond the raw line plot, highlighting both consistent cycles and anomalies. Try different periods or models, additive vs multiplicative, and see how the plots change. Let us see what happens if a date is missing and we attempt to resample. We make a copy to simulate mistakes. We remove the first row to simulate a missing date. We start a try-except block to watch for failures. We attempt to resample daily sums with the broken data. If it fails, we print the error message. The printed error reminds us why missing indexes can be risky. Running the cell now. How would you restore or fix the missing date for an intact analysis? Duplicate records can cause misleading spikes. Let us detect them in our data. We check the dataset for duplicate rows. We print out the count of duplicates found. Running the cell now. This output shows there are 0 duplicate transaction rows in the dataset, confirming the data is clean for analysis. Ensuring unique transactions is crucial before visualizing overall trends, so your line plot accurately reflects genuine daily changes without distortions from repeated records. This step supports reliable trend detection in the lesson's focus on transaction patterns over time. If there are duplicates, try removing them and observe the changes in your plots. For time series operations, the datetime index must be sorted. Let us check and fix if needed. We check if the index is in increasing date order. If not, we print a warning. We sort the index to make it ready for analysis. Otherwise, we confirm it is already sorted. We print that the index is sorted. Running the cell now. This output confirms that the data frame's datetime index is already sorted in ascending order, which is crucial for accurately plotting time series data. Ensuring the index is sorted prevents misleading visualizations when observing overall transaction trends daily. This step verifies data integrity before creating line plots to track changes smoothly over time. Why would resampling fail if the datetime index is unsorted? Best practices for transaction trend analysis. Always validate time columns and sort indexes before exploring trends. Visualize your data before applying models to spot seasonality or anomalies. Choose aggregation windows, for example, daily, weekly, that match your business questions. Be wary of missing weekends or holidays in test data. Remove duplicates and fill or explain missing periods for reliable results. Compare year-over-year or month-on-month changes for deeper business value. Running the cell now. Let us do a full example, find the busiest transaction day, analyze types of transactions, and plot its hourly activity. We identify which day had the highest transaction total. We pull the exact amount on that peak day. We print out the top day and value for business insight. We filter all transactions from that peak day. We count which transaction type appeared most on that day. We print the count of debit and credit transactions. We group by hour of the peak day to count activity per time. We make a small horizontal plot for hourly patterns. We plot the counts as a bar chart. We give it a clear title. We label our axis. We label count axis. We improve layout. We display the plot. Running the cell now. The output identifies January 21st, 2024, as the highest transaction volume day with $4,348.06, highlighting a daily aggregation aligned with our best practice of matching time windows to business questions. Notably, debit transactions outnumber credits, 14 versus 10, and the accompanying hourly bar chart reveals transaction patterns across the peak day, helping us spot key activity periods before deeper modeling. This illustrates the importance of validating and visualizing time-based trends to inform targeted analysis. Can you design a visual or summary for the lowest activity day? Subscribe on YouTube for more real banking Python projects. Try more. Next steps. Repeat these analyses on other customer segments or transaction channels. Build simple alerts for unusual peaks using thresholds. Share your visualizations with a team member and discuss likely business causes. Watch our YouTube channel for more Python banking tutorials. Running the cell now.